I'm Scott Henderson, for those of you I haven't met yet. Work at the University of Washington eScience Institute, and also I'm a research scientist in Earth and Space Sciences. So I'm excited to present today some additional content that David Shean started on yesterday. And as he mentioned, this is stuff that's sometimes covered in a quarter-long or even year-long course. So we're really giving a whirlwind tour of kind of geospatial analysis with Python in a very short amount of time. So appreciate you all bearing with us here and buckling up, because it's a bit of a race. But we wanted to just cover some fundamentals and kind of core concepts and give really practical examples that are useful for SnowEx. So today I'm going to start by focusing on raster data. Yesterday we mostly focused on vector data sets. And let me start sharing my screen. Make sure everyone can see it. All right. I think that's good to go. Can folks see my desktop now? See some nods. Great. I would really encourage people to interrupt me today. I would actually love it if I'm interrupted. It's hard on Zoom giving the presentations, right? And not knowing if folks are following along. So please feel free to unmute and interrupt. Also add questions in the Hackweek Help Slack. I'll try and watch those, but hopefully some of the other people can answer questions as they come up. So on our Hackweek website, under tutorials, under day 2, we have our geospatial fundamentals kind of subfolder. And the notebooks I'm going over today, actually, I'll probably just stick with this raster data link under here. So this is the notebook, and then I'll show you how to navigate to that on Jupyter Hub as well. But we pointed this out yesterday just on this geospatial fundamentals landing page. We provided links to some other content, and I do encourage people, if you're new to this, if maybe you have tons of experience with raster data in another language, and this is your first time exploring Python, this can be a lot to take in. So we've provided some links here to just other educational resources out there to explore on your own time. There's a lot of great content on there. So we've just provided 4 links. If you Google search, it can be overwhelming. So we tried to curate kind of a list of things that we would recommend looking at if you're getting started. And this raster data notebook, if you head to our Jupyter Hub, I think a lot of folks are logged in. I often get those messages you just saw that was like server error or something. And I find that refreshing the web page occasionally, if you've left it open for a while, tends to fix things. So just a tip there. So most folks cloned this website yesterday. I'm not going to go over that again. I'm assuming that you have this website folder already on your Jupyter Lab page. So we're going to open that up. Go under book, tutorials. There's a geospatial folder. So that's where we're at. You probably ran some of these notebooks yesterday. I'm going to open up this raster.ipynb. Things look a little bit different when you're running on the Jupyter Lab interface versus what's rendered on the web page. Just something to note. I think some folks were confused a bit yesterday about, do I have the same version? I don't see exactly what's on the web page. So just a note there that this website does a little bit of fancy rendering. So at the top here, we see our kind of learning objectives for this notebook, which is intended to be about a 30-minute overview of raster data with Python. And if you're looking on the web page, it shows up a little bit differently, but it's exactly the same content you're running. So just to make sure everyone's aware of that. So what we're going to do today is we're going to look at some different raster data formats. We're going to do a bit with reprojection, which David talked about yesterday is really critical to understand the coordinate reference system of data that you're using, especially when intercomparing data sets. So look at that for raster data as opposed to vector data. And I'm going to really lean heavily on two Python libraries for working with raster data, which are Rasterio and RioXArray. There are other libraries out there. These are two that David and I work with extensively. So just a caveat here, you're getting some of our opinions in this notebook, some of the things we use, and others may prefer different tools, but that's what we chose to do for these notebooks. All right, so fundamentally, raster data is a grid of values. Vector data that we worked with yesterday tended to be points, lines, or polygons, which you can represent in kind of their own distinct format, usually some sort of text file. JSON is what David talked about yesterday. Rasters tend to be gridded. So we're using images typically with rasters. Common example, right, is a satellite image, which is very similar to, for the optical satellites, an image taken from your camera. The difference being that you have some unique metadata embedded that links the pixels in that image to points on the ground. So that's really what we're referring to with a coordinate reference system, is this mapping of geospatial information contained within that image, such that you can put it somewhere on a map, right? You can locate it on the Earth. And the natural representation of images is a matrix. So often you'll hear us refer to these things as arrays. You know, it's a grid of numbers, really. That's what we're working with raster data in Python. And we'll see that often when you're doing any sort of computations, you're just going to be accessing this matrix of values directly and not necessarily worrying about the coordinate reference system. Okay, so to start off here, we have a cell that's just importing these libraries I mentioned, RioXArray, Rasterio, and a library called XArray. So let me run that cell. I want to walk through a couple things here, just line by line. So first of all, it's good to keep track of the versions you're using with Python libraries when you're doing analysis. Some of these libraries, as you can see by the version numbers down here, RioXArray is version 0.4.3. Anytime you see a 0 on a library version, it communicates that this is something that's under development. So it's important to realize during your calculations and what you're doing, which version you're using, because changes could happen to that library where your code maybe no longer runs. So keep track of the version numbers. That will ensure that your kind of notebooks or scientific code is reproducible in the future if you need to go back to a specific version as things change. Rasterio has been around much longer. So you can see this 1.2.6, it sort of communicates to you as a user of that library that this is unlikely to have significant changes after a 1.x version. And so you can be a little more confident in not having to worry so much about those versions. But anyways, as a best practice, just wanted to make sure people are aware of that kind of versioning system and what it means. The other thing I wanted to point out is the font size okay? Thumbs up for bigger, good. I'm gonna make it a little bit bigger. Okay, there we go. Other thing I wanted to point out, and this is just general rather than specific to raster data, is that this notebook is running in a temporary directory. So I've used the Python command oschdr to change the directory to/temp. This is pretty common on cloud systems or high performance computing HPC systems. It's referred to generally as a scratch space on the computer, which will disappear when you're done running your computations. Everyone has a limited amount of permanent storage in their home directory, but it's quite limited. It's 10 gigabytes in this case. So as you start to work with larger data sets, and often raster data tends to take up a lot of space on your disk, you can work in temporary directories and avoid running out of space. So that's why we're doing that. And then a couple other just things that you can try, some things that I like to use when working with Jupyter notebooks. There are these percent commands, which are specific to Jupyter notebooks. You can't run this necessarily in a Python script, so just to be aware of that. These are configurations for the appearance of the notebook or special commands. And this one here, figure format retina, makes the fonts appear better on kind of modern monitors. So that's what that line's doing. There are also ways to make font sizes bigger in your figures. So throughout this notebook, I'm going to kind of go over some tips of just the Jupyter interface in general and running things in these notebooks. So just wanted to point that out as well. All right. Actually, if I could do another quick Zoom poll to see how many people have used one of the libraries I've mentioned for work in the past. So Rasterio or Rio X-ray, if you could do the hand raise or the thumbs down for no, that would be helpful just to see. All right. Cool. Got some claps, a couple thumbs downs. I'm glad to see some thumbs down. We're sort of coming at this assuming that you may have seen these libraries before, but you're not necessarily using them regularly. All right. That's helpful to know. Thanks. All right. So the rasters we're going to work with in this notebook, I just picked elevation data. This will, I think, be useful for folks just making visualizations, making a base map to put their other data on top of, or thinking about comparing different elevation data. So the first data set we'll look at is from NASA as the NASA DEM. So this is from the Shuttle Radar Topography mission that flew back in 2000. It's important to always think of the date of the digital elevation model you're using, right? Especially with doing inner comparisons. So this is kind of a gold standard in global, almost global elevation data. It doesn't cover high latitudes or low latitudes, but it's been around for a long time, and it's a widely used elevation data set. So you can read more about that here. I'm not going to go into details. The way I found this link here, which is a link to one of the NASA archive centers, is just going to Earth Data Search. I think we covered this a little bit. I think Amy mentioned it in her tutorial talking about an SIDC. This searches all of NASA's holdings. So if you're looking for a specific data set, you can go here, navigate, and find URLs when you start drilling into data that you locate. Okay, so that's where that comes from. And this line here requires that you have a netrc file in your home directory. So if you run that cell, we are using a wget command. Again, the exclamation points in a Jupyter notebook will execute a command as if you're running it in a Linux terminal. So it's equivalent to opening a terminal and typing a wget command in the terminal. Hopefully that works. Did that command run for other people?
It's not running for me, Scott. The whole link is down when you click it.
Oh, really? Let me just go to a web page here and see how that goes. Ah, strange. All right, just a moment. All right, so maybe that server is just not working currently. All right, no worries. Happens. Sometimes servers are down, right? Which is that's okay. So if we just interrupt kernel, if you go up to kernel, interrupt kernel, whenever you have cells hanging like that, that aren't executing, you can stop the execution and move on. I'm just going to go back to the rendered version. It seems like that it's a USGS server in this case. It's actually just not operational right now. So ideally, what you'd see running that is if you're able to retrieve the data, it's a zipped file. It's an elevation tile. So it covers a 1 degree by 1 degree grid. We unzip it. We see that we have some different files contained in there. There's a .hgt, which is raster format. And I'll just go through what these cells do without actually running them. So the Rasterio library reads in a ton of different elevation formats. Behind the scenes, it's using a library that's been around for decades called Gdal. David mentioned this yesterday. It's a geospatial data abstraction library. It's able to read a lot of formats and has code to do coordinate transformation, warping, conversion of formats, etc. The way you typically open data sets with Rasterio is using a statement that's called a context manager in Python. So folks may not be familiar with this if you're new to Python. What it does is if you open a file in this way, it is going to automatically close a reference to that file for you. You'll see in some other kind of older examples, or if you're used to older programs, you often have to do a file open, run computations, and then always remember to do a file.close command at the end to make sure the connection is closed. These context managers do some other things, but they also automatically do that kind of opening and closing for you. And I'm printing here a profile of that raster data set, which gives you a summary of its, its attributes. So you can see the driver is SRTM HGT. That's the Gdal driver being used to understand how to access the data as it's written. There's a data type, which is an integer 16 data type. You'll see floating point values, integers, complex values, and rasters. We also have a no data value reported, the width and height. So this data is a matrix 3601 by 3601. And then the CRS. So we've seen this before. We saw this yesterday. It's EPSG codes, and then affine transformation matrix, which is this linking of the matrix, this 3600 by 3600 matrix, to its location on the Earth. So in this case, we have basically a latitude and longitude affine transformation matrix to put this data somewhere on the Earth. Okay, that's just a metadata summary. You can also use some tools built into Rasterio to plot the data or to read it into a array in Python. When you're working with arrays in Python, you use the NumPy library. So what I'm doing here in this first line is I'm opening that raster data set, and then I'm using a read command to bring in all the data values into an array, into a matrix. This next line here, prints the type of the data, is showing you that that object in Python is a NumPy array. That's the printout down here, class NumPy. And then I'm using the matplotlib library that we imported earlier to actually plot that array. So what do you see down here? These are just your row and column values. As we know, it's 3,600 by 3,600. I've printed out the dataset name, and then we have the values here, which are elevation values in meters. So this is covering a bit of Grand Mesa, not all of Grand Mesa, but you can see the elevation showing up here in this plot. Often geospatial libraries have some built-in conveniences. So, it'd be more convenient probably to see what are the latitude and longitude values rather than the row and column. Rasterio has a built-in plot function, so rasterio.plot. And if we use that built-in plotting functionality, it automatically puts on the coordinate values. So now we're looking at latitudes and longitudes. Instead of up above, we had the row and column. So with raster data analysis, you're often doing this jumping back and forth between the row and column, and then the geocoded coordinates on the ground. And finally,
Scott,
yep.
I just have a quick question. So I only started using Raster.io when I was setting up my tutorial. And one thing I found with Rasterio Plot compared to just a simple like matplot on raster data is you couldn't have a color bar with the Rasterio Plot. Is this correct?
You can, but you have to kind of jump through some hoops to do it. Let me try this one more time and see if I can grab that data set. No.
I have a question too, Scott, just a simple one. In a lot of Raster.io code I've seen, they use the as src, and I was just wondering what that means because it's used in a lot of examples online as well.
Yeah, so I'll get to both questions here. Yeah, so I would say first, I guess rasterio.plot, that built-in functionality is kind of to give you just a quick view of the data where you don't care about color bars customization. You just want to like quickly view it. And if you do want to customize it, add the color bar, etc., what people tend to do is read in the data like we did before as a NumPy array, and then do all your customizations through matplotlib, such that you can add color bars, change the axes, do all that stuff more directly. But this context manager approach is what they recommend in Rasterio to do the automatic closing of data sets. You can also do other things like set variables that apply only as you're operating on that data set. So this comes into play if you're working with many different raster data sets and want specific options to apply only to the operations for that data set. You can do things with Python context managers such that those options only apply within this block. So that's kind of why you're using it. But you could call this anything. You could call this with Rasterio open as file, and then refer to it down here as file.read. I don't know why they use src for source. Is just some canonical thing that's in their documentation. So hopefully that answers some questions. I think with this next data set, let me try to get, since we've got a bit of time, let's just try and get a different raster. So I'm going to go back to Earth Data Search. And then we'll see if this works. So I'm going to zoom into Grand Mesa. draw a box around Grand Mesa and then search for SRTM or NASA DEM. All right, and here you can see there are these 4 elevation tiles, right, intersecting the search box that we did. Let me just see, which one did I use before? So 39109. So the way I did this before was view details. And then in here, you'll find a link to the actual data. Sorry, this doesn't look, it's probably really hard to see. Let me just try. Occasionally these links change, right? Which is a little bit frustrating, but let me try to download that one more time. Yeah, it's just not working. Okay, let me try getting a different data set. So NASA DEM is kind of derived from Shuttle Radar Topography Mission. Let's go ahead and search for that. And try to download one of those. Yeah, that's not working either. All right, skip that. I think we'll be okay because down below here, I use a different data set. So I'm just gonna move down this notebook and actually open a file so that I can show you some of these things that people are asking about. So in this notebook, we've just gone over the Rasterio bit. This next section talks about Rio X-ray. And I think this is best illustrated through example. So I'm gonna cruise down this notebook to where we open a different data set, the Copernicus digital elevation model. So this is newer digital elevation data that's from the European Space Agency. It's hosted on AWS as an open data set. So you can click on this link to read more about the data and some more documentation of where it's hosted. Important thing to note with Copernicus DEM is this derived from the Tandem X mission, which was kind of European mission to do a global elevation data set. So this is a more recent data set, I believe from 2010, I don't know, I have to double check, 2010 onwards, and scenes taken from X-band radar. All right, so instead of a link to that USGS server, we have an S3 link here. So this is a data set stored on Amazon storage, and we can work with that data and start using some of these tools. So this command here is a command line utility to access data stored on S3. S3 is a network storage system, kind of like Google Drive. If you use that, there are a lot of cloud-based storage systems where you can host data that's accessible on a network. So it's basically a little server out there that's giving you this data. And this is a TIFF file. You can see we just downloaded it. It's basically a 1 degree by 1 degree grid, just like SRTM. So just to illustrate some of that stuff from before, if I do with Raster.io, open, I'm going to give it this link here, Copernicus DEM as source. we can print the profile. Oh, I just listed it. Sorry. Yeah, let me just copy it. Second. So this upper command here, I'm doing an S3. Sorry. Go back. S3ls. That just lists the file. I actually want to copy it to my local directory to work with. So what we can do is S3 copy and then put that file in the current directory, which is done with that period. So that actually copied the file. And now I'm just going to open it like we did before with the SRTM data and print out this profile. And here you can see driver geotiff instead of this SRTM HTT. There are all these different raster formats out there. It's a different data type. Now we have a float 32 data type. There's no data set for this raster. But it does have the same CRS. All right, so that was copying that file locally on a disk and reading it. One really powerful thing you can do with these libraries is you can read data directly from network storage. So instead of doing that copy to the local disk and reading it, we're just going to read it on the server that it's sitting on. And what's actually going to happen is you're just streaming the information into your computer memory rather than writing a copy of the file to disk first and then opening it. So this is a very important concept, I think, especially for using kind of cloud servers and thinking about ways that you can access data regardless of the machine you're running on, where you do not have to do this first find, download, store step that we're all accustomed to. It takes a little bit more settings. So let me walk you through what's happening in this cell. The URL we saw above is basically like an HTTPS link to a website. The only difference here is that it's stored at this S3 location. So I'm pointing towards Copernicus DEM and the location of that file. We're still using the Rasterio library, but Rasterio was sort of designed initially to work with data sets sitting on a hard drive. And it has newer functionality to read data sets that are on a network. So when you're doing that, you often have to set up a few additional environment variables to get things to work. So that's what we're doing here. And this gets to Jack's question about why use these context managers. We set up an environment that applies to a specific situation. In this case, we're reading from AWS storage. And we set some environment variables that allow us to do that. The first one is so that you don't list everything in the directory you're reading from. This is something that's really common for reading from a disk, but it's super slow when you're reading from things on a network because you have to list every file under a directory. So that's just an optional setting to speed things up. And then we're telling Rasterio to not send any credentials. This data set's fully public. So unlike using a netrc or using some sort of authentication, you can just read public data. It's open to anyone. So that's what the second setting is doing. And then finally, we use that environment to open the raster data. So that's why we have this context manager approach. We're using that environment, and then we're opening that URL directly. And this should show us exactly the same profile that we got before, because we're just reading the metadata in this file. We're not downloading the whole thing first, so it's very fast to give you that information back. So that's Raster.io. Next, I'm going to show you a library called RioXArray that builds on top of Raster.io. So these libraries are kind of a pyramid approach where they're building one on top of the other. And RioXArray is a great library that really makes a lot of raster operations pretty, I guess, intuitive. So we still use that same context manager approach. And then we are using this library to open an XArray data array. So you saw this, I think, actually, this is probably the first time folks have seen this. Let's do another maybe hand raise. Has everyone seen who's worked with raster data, a XArray data array? Thumbs up or thumbs down? Cool, so we've got more thumbs down now. And all right, so let me walk through this for a second. I apologize for the kind of going back and forth. Not having that first data set kind of threw me for a loop, but there is some documentation in this notebook for RioXArray. What it is, XArray is a library that's designed to sort of extend NumPy, which works with arrays, to work with multidimensional data and add handling of indexes, kind of like you do with pandas, like we saw yesterday. So it's blending kind of the best of all these existing libraries to work with either two-dimensional rasters, like we just saw, which is a matrix, or starting to extend into tensors, multidimensional data, where maybe you have now stacks of satellite imagery in time, or maybe you have a raster data set that combines different data variables. So instead of just elevation, maybe you also have on the same grid, temperature, precipitation, snow depth, right? Different data variables that you're starting to store in the same container. So that's the idea with XArray. All right. So this XArray object is called a data array. And you can see the printout of it here is a little more informative than I think kind of the text you get back from some of these other libraries. It's a little more intuitive what it is you're working with, where you're shown the dimensions of the data, but also the coordinate values. In this case, we have latitude and longitude. Okay. XArray is also nice to use because you have some special plotting tools that we saw yesterday from David that build on top of it. So this next cell, in order to run it, I'm adding a line, import hvplot.xarray. This is very similar to the line we saw earlier from Rasterio, which was kind of a built-in special plotting method. And it is earlier in the notebook, but because we didn't have that USGS data set, I didn't actually run it. So I'm going to import that library here and then run a plotting commands, which is hvplot.image. And I'll walk through what each of these things is doing here. So this looks pretty similar to earlier. We have already seen, sorry, on the rendered version of the web page, which I'll go back to, maybe. Shoot. Sorry, struggling with Zoom there. The SRTM data. here we're showing the Copernicus DEM elevation values. Again, we have meters. This plot, as you can see, if you're running this, hopefully folks are kind of going through this simultaneously, is giving you some interactive feedback for where you're at as you move this cursor. So we see the X position, Y position, which is longitude, latitude, and then the elevation value as we pan around. So this built-in plotting functionality is really good, I think, for interactive analysis of raster data, where especially when you're running things in this JupyterLab interface, because you have that interactive feedback. Because it's designed for multi-dimensional data, we have to pass explicitly, this seems a little odd, awkward, we're saying X equals X here. That's because with these X-ray data sets, you might instead have latitude, longitude, X, Y, Z. You can have different values for your dimensions. And so it's sometimes good to just be explicit about what do you want on your X-axis, what do you want on your Y-axis. This keyword flag is not necessarily obvious when you're first using this library, but it's very important for visualizing raster data in a web browser. So what it does is raster data can be quite big. You can have matrices that are many thousands of pixels by many thousands of pixels. And if you try and put all that data into your web browser, which happens when you're using libraries like matplotlib, it can be a lot of data. You can try and visualize full gigabyte data sets in your browser, and then things tend to crash. So this is kind of built into this plotting library where you're actually only sending rendered versions of the raster data set to the web browser to visualize it. That also means that as you zoom into these raster data sets, the resolution will update on the fly. So if I zoom into a specific area, you can see the elevation is re-rendered at a higher resolution. So that's using this box feature over here on the right. This reset button shows, kind of looks like a browser refresh, will take you back to the original view. So like I said, these utilities are especially good, I think, for interactive visualization, exploring data sets. If you're making a figure for like a paper and you want full customization of the color bar, and you know exactly the bounds you want to use, et cetera, then matplotlib is a great library to use for that level of customization. All right, let me just check in there. It looks like some folks are having some errors with trying to run things. Any questions? That was a lot in this last section here. So.
I had a quick question, Scott.
Yeah.
What if you, I don't know if Rasterio, you can do that with Rasterio, but what if you converted your TIFF to like a CSV and then exported it? Do you think that would be something to help like memory? Because you mentioned running things over a server and the size of images. I don't know if you think that could be like a workaround that.
Yeah, so CSV would be, I guess, a vector format where you have kind of point by point a storage of value, and some people advocate for that. It's like LiDAR data sets often it's just store all the points with their corresponding latitude and longitude in a table. CSV or other kind of vector format, but there are data types that work pretty well for reading even large data sets over a network, and one of them is a GeoTIFF. So if I go back to this line here, this data set is 60 megabytes, I think. And when we run this cell to open the URL, it's almost instantaneous. It takes about milliseconds to construct the data set because you're only having to read the metadata. When you actually do a plot like this, then you're actually grabbing all those 60 megabytes and presenting it in the web browser. So formats, raster formats like TIFF are quite good, I think, for storing on a network.
Okay, all right, thank you.
Mm-hmm.
I guess as well, when you have a regular area, but a CSV or an ASCII file or something, you're actually saving a lot of NANs. So it takes up a lot more memory than a TIFF. So that's another reason to advocate for TIFFs instead of a basic text type file.
Yeah, great point. All right, let me do a couple other demonstrations, and then we'll have a time to just like maybe work on stuff in a bit of an exercise. Another reason I really like this Rio X-array library and why I advocate for people using it is that it makes reprojection very kind of transparent and easy. So gosh, this is actually going to be a little frustrating without that NASA data set. So let me go back to the rendered version on the website. Just a second. Yeah, so let me just walk through here. Again, this is the NASA DEM data earlier in the notebook, and I'm going back to the rendered version. So we've loaded that with Rasterio. Then I illustrate doing the same thing with Rio X-array, where you load the NASA DEM into this X-ray container we've just looked at. And again, you can do the same kind of interactive visualization. You can also use this Rio X-array library to do selections. So this is something that didn't show yet, but let's say you wanted a profile at a specific latitude. The syntax is pretty straightforward for doing this in the Rio X-array library. It's sort of like pandas, where you have, that we saw yesterday, we had a .loc command to get a specific location, or an iLOC to get a specific row or column. It's the same idea with X-array. You can use a .sel, which is for select, and then pass in the coordinate you want to select from. I'm also passing a keyword here, nearest, because maybe 39.3 doesn't exist exactly in the coordinates, and this will grab the nearest one. For example, if your grid was set up such that you had 39.2, 39.5, this is going to grab 39.2 from your grid. And we can plot profiles. Same library here, this HB plot, such that you're now getting some more interactive feedback as you explore the data. So I'm just plotting an elevation profile here. And what I wanted to illustrate with this NASA DEM is that it's quite straightforward to reproject to a different coordinate reference system. So we saw earlier that this was an EPSG 4326. It's kind of the classic latitude, longitude, unprojected coordinates. And let's say we want to put this on a UTM coordinate reference, like we did yesterday with the vector data. You have the ability to do that with just a reproject command. So this is the equivalent of what we saw yesterday in GeoPandas. There was a toCRS command to change the CRS. With this library, it's the X-ray data set, which I've called DA from up above. Yeah, when I opened it, just to remind people, when I opened this data set in the beginning, I called it DA. And again, this is sort of a choice. You can call it whatever you want. I tend to call it DA for data array, which is the type of data that it is. So once you've done that, you have these built-in functions, for example, to reproject. So I'm just passing the EPSG code for UTM 12, I believe, from yesterday. And then you get a new object back that's reprojected in that CRS. So here you can see that the dimensions changed, right? Now instead of 3600 by 3600, we've got slightly different dimensions because we've changed the coordinate reference system of the raster data. And if you plot it, you can kind of see why that is. So this is the reprojected data, now HV plot. Now our X coordinate and Y coordinates are in meters instead of latitude, longitude, but we still have our elevation values. And the whole grid is sort of rotated in order to get it into the UTM coordinate system. So that's, I think, a very convenient syntax for doing these reprojections of rasters. And finally, if you want, you can also save this output to a format on the disk. So we open this file from a network, we did a bunch of transformations to it. Maybe we want to save a copy locally. This Rio X-ray library has a toRaster function, and we just give it the name. So in this case, I'm calling it the same name, but with the EPSG code, just to remind myself what it is. For the driver, there's a link here to explain what this driver is. Again, this is there's so many raster formats out there and tons of drivers you can use. This one is one I like to use a lot, which is for cloud optimized GeoTIFF. And there's a link there to learn more about that data format. So that's kind of a whirlwind tour of like the most common things I think people do with raster data, which is open it, view it, take a profile, reproject it, and then maybe save it. I think that covers like 90% of workflows that you do with the raster data, at least initially when you're exploring it. All right. Question?
I have a question.
Yeah.
So if you read this multispectral satellite data, can you create the color RGB image?
Yeah, definitely. Again, this is where I like these libraries that work well with multidimensional data sets. So, I don't have a good illustration of that in this notebook right here, but let's say your raster that you're opening has multiple bands. Mm-hmm. When you do this open here, this is something I didn't really talk about. Let me go back. So I'm going to rerun this cell here where I open that URL. And again, this is for the Copernicus data that's actually available to us. And I'm commenting out the last bit of code that I had here, which I'll explain what that does. So I had this little bit of code here that says squeeze band drop equals true. X-ray, as I mentioned before, is designed to work with multidimensional data. So whether it's multispectral, whether it's like a net CDF that has different data variables, it wants to give you back a 3D or 4D ND object. And that's why by default, you get a band equals 1 coming back when you open these data sets. A lot of raster data is 2D, like these elevation data sets. There's just one band. It's just a 2D matrix of raster of elevation values. And so often this is just a bit of an inconvenience where I don't really want to keep track of that extra 1. So I tend to run that squeeze bands to just get rid of it because it's 1. But if you had multidimensional data like red, green, blue, near infrared, whatever, you can open these things such that they're all there in this container, and then create an RGB image if you want.
Thank you.
Okay, there are a few more things I wanted to cover with the comparing of 2 data sets. And again, I'm going to go back to the rendered version since we don't have, unfortunately, the NASA one, and I didn't make a local copy of it beforehand. But this is something that's, I think, going to be really important for projects working with different raster data sets. So what I want to illustrate here is how do you compare two? In this case, the NASA DEM with the Copernicus DEM. I'd like to do a difference between those, but I'm not sure they're on exactly the same grid with exactly the same coordinate reference. So the way you do that with this Rio X-array library is using a built-in function, and that function is called reproject match. So what's happening here is that in this notebook, we loaded the Copernicus DEM. I called it DEAC when I opened that up. And we have our DA object, which is the NASA DEM from earlier. This reproject match function takes the Copernicus elevation in this case, and it's going to reproject it to match the NASA DEM. So it's nice because you don't really have to dig into the details of what exactly are these grids and how do I align them manually. This library is going to do that for you. And it's going to give you back a reprojected version. So that's what I've done here. This DAR is reprojected to match the NASA DEM. And I'm just printing out the values again of that data set. So once you've done that, now you have two rasters that you know are aligned, that have the same grid, and you can start doing things like taking differences, maybe drilling through to compare specific pixels, etc. And so that's what we're doing here. We're just doing a subtraction of these two rasters and then plotting the difference. And you can see now this is in meters, the color bar here, and we can look in specific areas, zoom in on wherever we have maybe more anomalies, try and figure out what's going on if we do differences. You can also do things like just take, look at histograms instead of the map view. It's often better to visualize data as a histogram. And so here I'm plotting the histogram of that difference and trying to understand these, match up pretty well. The mean value here is also plotted. It's not quite 0. And as you can see, there seems to be a little bit of a bias in the kind of positive bias values up here. Grand Mesa, which is quite flat, the elevation differences are almost negligible, right? Because the differences tend to be due to geometric differences, et cetera, and steep regions with elevation data. And then maybe folks have read ahead a bit, but what's something that I still have not accounted for in doing this difference? Is anyone like, oh, don't do that? Or is this the first time folks have seen differencing elevation data? So I'll go ahead and continue on with the notebook. It's like no one's chiming in. This is a subtle thing, pretty advanced. So if you haven't seen this, no worries at all. When we looked earlier at the coordinate reference, we saw that both of these data sets were latitude, longitude, EPSG 4326. So this tends to be a latitude, longitude, and then every grid pixel is an elevation value in meters. Awesome, thanks, Jessica. Jessica's chimed in on the Slack channel and says, did you check that they're the same datum? So this is something we talked about, I think David talked about briefly yesterday, but it's very important to keep in mind with comparing data sets, especially elevation data. And the question is, what is your 3D reference? What is the elevation itself with respect to, not just where is it in terms of latitude and longitude? So there are kind of two options with elevation data. You can reference to an Earth ellipsoid, which is a model of the Earth, a mathematical model to simplify things. And this ellipsoid surface is very common for geodetic applications. If you're doing SAR processing, you want some kind of mathematically simple surface to operate against. And so you'll often find data sets that are referenced to an ellipsoid. You'll also find elevation data that's referenced to a geoid, which is a gravitational equipotential surface. That sounds fancy, but what it means is where is sea level? So think about elevation data on the coast. And if you're walking on the beach, you expect that elevation to be 0, right? 0 meters, because you're at sea level, and then maybe negative being below sea level. So this is a subtle thing when you're on Grand Mesa in the mountains of Colorado. It's like, where's the 0? And I like to think of it though as just, I always think of on the beach. Geoid is on the beach relative to sea level. Where is that equipotential surface where water surface is at on the Earth? And that's going to vary around the globe. So you actually kind of have to dig into the details often with data sets to understand what is their 3D datum. If I go back up to the top of this rendered notebook to the NASA elevation data, there's a link here to the data product information. I'm going to open that link. Gosh, I guess none of these are working.
Hey, Scott, could you summarize the geoid ellipsoid thing again, just like you did a second ago?
Yeah, sure. Let me go back down. In this rendered notebook here, I also have this kind of like warning statement with a bit of this description in text. But the way I think about this is an ellipsoid elevation values relative to mathematical model of the Earth's surface. So that's going to be your 0. A geoid is an equipotential surface. So where is, if you had an Earth that's just water and different, a different gravitational field, that water is going to fill in a non-uniform way a surface that's an equipotential surface. It's along a line of in the gravitational field. So this is a kind of like a spatially varying surface is the geoid, versus the ellipsoid is going to be just a mathematically uniform surface. The elevation data though is with reference to that surface. So you want to know, is your elevation data referenced to an ellipsoid, or is it referenced to a geoid surface? Hopefully that.
Thank you.
Yeah, sure. It's definitely confusing, but if you dig into those details, and unfortunately the documentation page is also down, you'll see that for NASA DEM, the data is WGES84/EGM96. EGM96 is a gravitational model. So it is this equipotential surface that those elevation values are given in. And often with elevation data like these, like I said, you expect 0 to be sea level. So they're often given with reference to a geoid. The Copernicus DEM uses EGM 2008. So this is an updated geoid model at a future date in 2008. There's a lot of talk on some of these libraries, and as you get into the geodesy, which is studying the shape of the Earth, and people get very technical about this stuff and talk about temporally varying 3D coordinates rather than the 2D coordinates. There's a lot of kind of chatter about how to do this exactly right. But I think it's good to just visualize what these shifts can look like. So EGM 96 and EGM 2008 are actually very, very similar. And that's part of the reason if you just directly difference these two data sets, NASA DEM and Copernicus DEM, we see kind of a pretty good agreement here with these two data sets. However, if you did that same difference and one of those data sets was referenced to an ellipsoid rather than the geoid, you can get hundreds of meters of difference. And so this is very important to recognize if you are comparing data sets. There are ways to shift the data, there are basically these datum shift grids that allow you to convert ellipsoid heights to geoid heights. And I'm showing here that you can access those grids. Again, they're just rasters, where each raster grid value is a shift that you should apply to your data set. And I'm opening here the EGM 96 grid, which is available online, and just plotting it like we did before. So here, plotting this datum grid shift, which is an ellipsoid height to EGM 96 geoid height, you can see the variability globally. And you get variations up to, over 100 meters, depending on where you're at on the globe with these shifts. So, yeah, and there's a bit of talk on the Hackweek Help about, looks like how different, often different data types and data collections will use different ellipsoids, different geoids. So I definitely just wanted to make everyone aware of how you deal with this with raster data. Questions at this point?
Scott, you mentioned that you can use this raster that shows the differences between the datums. How do you go about converting the two or converting one to the other?
Sure. Yeah. So I think I maybe said I left it as an exercise, which is misspelled, it looks like. But in brief, right, this grid here represents a WGS 84 to EGM 96. So it's you would just do basically a sum of these rasters. And a key thing though is, maybe I'll pose it as a question, right? Before, when we were looking at the difference here, there was a key step we did before this difference. And so did folks follow that step before taking the difference in two rasters?
Reproject, right?
Yeah, exactly. So that datum shift grid is just another raster, right? And what you want to do is you want to find the values for whatever raster you're shifting. And so what you would want to do is reproject match for the datum grid, and then either add or subtract. If your raster is an ellipsoid height, then you would add. You would go add this grid, right, which is WGS 84 to EGM. You're shifting it to the datum. But if you wanted to go the other way, you would subtract. So if you wanted to go from geoid to ellipsoid height, you would subtract the grid. Hopefully I got that right. There are also some libraries that do this automatically for you. So you may have come across command line utilities that we didn't really talk about, like sorry, so Gdal Warp is a command line tool that's in the Gdal libraries, kind of used behind the scenes with these higher level Python libraries. And some of these are set up such that they can do these shifts for you. I haven't illustrated that in code here, but not all libraries. I think if you did, for example, as you could see earlier, this library is recognizing this data set in its 2D coordinates, EPSG 4326. EPSG 4979 is a 3D, is reference to a 3D coordinate system. So depending on how the raster is stored and whether the library is capable of understanding these 3D coordinates, you might be able to do a reproject and pass in the 3D, if it starts in a 3D reference and then to a 3D reference, sometimes the software libraries can take care of that for you so that you don't have to do the mental exercise of figuring out, do I add, subtract, do this reprojection myself. Okay, I think I wanted to check if David Shean's joined us and if he wanted to cover a little bit more with SnowTel. Otherwise, I think it'd be great to just maybe break into small groups and experiment. Is David joined us?
Yeah, I'm here. I made it.
Okay.
Can you hear me?
Yep.
Well, we have a break coming up, right?
I think in 15.
Okay, and is it a 15-minute break?
It's going to be a 30-minute break starting at 10:30.
Okay. I don't know. What do people think? Are people saturated? I mean, we didn't finish the SnowTel stuff, and I can also mention a kind of hidden notebook that is not ready for inclusion in the Jupyter book, but has some other examples of how to fetch DEMs and do some of this stuff on the fly. So maybe that would be a good use of the next 10 minutes. I see a few people nodding their heads. Okay.
Sounds good.
Okay. Cool. Well, then I guess I will jump in and share my screen. Scott, I think you may need to stop sharing.
Sorry. Sorry, I don't know where my controls went. And
as you're doing that, I'll just talk about, so follow up on the datum and coordinate system stuff.
Yeah, thanks.
This stuff is infinitely confusing, and there's a lot of reasons for that. There's a lot of history behind these definitions. So the field of geodesy, people have been trying to measure the shape and surface of the earth for hundreds of years, thousands of years, really. I mean, it goes back to like ancient Egypt when they were trying to estimate the shape of the earth. And our ability to do that, to measure these things, has gotten better and better. But a lot of these datums were initially defined by tide gauges, right? We're trying to find some mean sea level. And as we know now, you can't do that. The mean sea level on the East Coast versus the West Coast versus some other part of the planet, it's not the same. And it's changing all the time too, with sea level rise and with other dynamic components. So the satellite era has made it both better and worse, because now we can get a much better handle, like with the GNSS networks, like the GPS network. We can very precisely measure the shape of the Earth, and we can measure how that's changing. But then doing these conversions back to these old systems that are just wrong in a lot of places, they're off by many meters in some cases. And it's not just a simple vertical offset, there's also the horizontal offsets. So it's confusing, don't worry. There are good resources, and I'll just point out that here, desktop, let me share here. So the official, for at least the United States, the official, are people seeing my screen?
Yep.
I've got a website up. Okay. The National Geodetic Survey under NOAA is the official body that does this for the US, along with NGA, the National Geospatial Intelligence Agency. So they're the ones who define those EGM things. That's a geode model, One of them was from 1996. The most recent one is from 2008. It's gotten better. It's higher spatial resolution, so it's a finer, horizontal capture of this equipotential surface. This what would be mean sea level if there were no continents. It's our best ability to do that. But anyway, I wanted to point this out that the NGS, the current datum that's defined for the United States, this is what all the federal agencies and technically, I guess, NASA is supposed to be using, is this NAD 83 ellipsoid. And you see here there's an epoch, because to make things even more complicated, we've got these plates, right? Plate tectonics. And the North American plate is moving about 2 centimeters a year westward relative to some reference frame for the Earth, as are all the other plates around the globe. And so what this North American datum, this 1983 thing, which is what the database is using, it tries to stay fixed on that North American plate. So in other words, you don't have to worry about that 2 centimeter per year shift. If you go out and you make another measurement on Grand Mesa at the same benchmark on the ground, it should be in the same place. But there's this whole problem of a satellite doesn't care about that. And so time starts to matter here. So anyway, the one thing I will say is that there are efforts underway to update these things. We're replacing these older systems that were largely done with people going out with levels and setting up instruments on tripods and measuring things across the United States. And this will be much more in line with these more modern satellite-based reference systems. So it's confusing. These aren't going to go away. A lot of the data are going to stay in these older coordinate systems. So you got to kind of know how to work with them and how to convert them to newer things. But as we move forward, starting in 2022, probably realistically 2023, it was delayed a little bit by COVID, but it should get simpler. So at least there's some hope here in terms of coordinate systems and data. Okay, so I've got 5 minutes, so I'm gonna do my best to catch up here. So as a reminder, yesterday we ran through the SnowTel notebook and we found a bunch of points by querying this Kawasi API. And if we scroll down here, we isolated a handful of those for Grand Mesa. We did this visualization here. So thanks Scott for going through some of the nuances of this HV plot. I just kind of blew past that. People were like, whoa, how'd you zoom? So now you know, you can use these little features over here. And I encourage you to play a little bit more with some of that stuff. So we left off here. So we were going to try and get the time series data for one of these SnowTel sites. And I think I ended up going with the Park Reservoir one because it's a little longer. And there was some discussion on the Slack channel about which one is most representative. I think that's a really cool thing for people to follow up on. So looking at some of the snow depth grids and try to look at the differences at each of these sites for what we expect for how snow depth varies on the Grand Mesa. But for now, we'll just grab this one, 682. So that should be this Park Reservoir one. And we left off here where I kind of ran through this and said, look at all the things we can measure. And there was a bunch of follow-up about maybe you shouldn't trust the temperature or the precip. And there's some nice information. People shared some papers on how to correct some of these things. But if you do need some simple AWS data, automated weather station, you can play with some of those. But we're just going to work with the snow depth or the snow water equivalent variable. And actually this snow water equivalent, usually these records are much longer. So they go back, 40 years, maybe 50 years in some cases. Well, probably about 40 years, let's just say. Whereas some of the snow depth measurements, that's a, kind of an ultrasonic ranging sensor. And those have, in a lot of stations, they weren't installed, 10, 15 years ago. So some of them are a little longer, but since a lot of our measurements we're dealing with LiDAR or other ISAT or other things, they're looking at the surface. So we're going to use this snow depth variable. But I encourage you to go back and rerun this with the water equivalent, and that will give you sweep as opposed to just meters, or in this case, this will return inches. So you're gonna have to do some unit conversions there. Okay, there are hourly, I haven't spent much time with them. Maybe some people can comment on that, but I think the daily is generally what we wanna work with. So what we're going to do here, we're going to run this get variable info. We're passing in that same API endpoint, and then the variable code, which I defined right here. And we see that this SNWD is a snow. There's a no data value. It's a snow depth measurement. And we see down here, it's daily. So, so there's a lot of codes and things in here. It takes a minute to parse this. And then the units of the values are going to be in inches. So that's code 49 and some definition. So we're going to get snow depth inches every day. Okay. And what I did here, I wrote some code. I'm not going to go through all this, but this basically, it's a function that takes the site code, the variable, and by default, I'm using the depth, a start and an end date. And it will return a data frame of all of the values between those time periods. So we're just going to define that function. And here I put in, we're just going to go back to some arbitrarily old date. I think it should work without this, but there's no SNOTEL sites in 1950. So it's a dummy start date. Okay, and here we're actually going to run this thing with that site code, snow depth, and then those definitions. Should take a second. And of course, the curse of the live demo. All right, that's better. And I think we're all going to be hitting some public server at the same time again. If it doesn't work for you, maybe try rerunning and it should be fine. So what we have now is a pandas data frame. So this isn't a geodata frame. We don't have any coordinates, but starting in 1997, so they installed the Sonic Ranger May 21st or March 21st, March 22nd, and then here's the value. So that's the snow depth that was measured in inches on that day. So if we keep kind of running through here, we see there's 24 years of these snow depth measurements, and there's our quick visualization of the data frame. And these are our snow depth measurements starting back in like 1997. You can see the annual measurements. There is missing data in here. Up here in this function, I throw out some things that don't have, I only keep the highest quality control level. You might go back and play with this and just see what is in there that is flagged as bad, but is actually not a bad measurement. But you can see we should get data up into, a few days ago. We zoom in here. So we zoom in kind of, here's the most recent record, and we should be getting something from the past few days. So this is the most recent snow depth measurements for the 2020-2021 season. And we're running out of time, so of course I will blow through this here. This is a function to add the day of water year and day of year to our data frame. We'll do that, and say values df. We should see new columns added over here with our day of year and day of water year for each of these days. And we'll do the classic kind of, let's look at the day of water year and the statistics for snow depth on each day of the water year. So we'll get mean and median value, some idea of the spread across that 24-year time period. And we plot those up. We start to get something that looks like something you may recognize, where we have snow depth here on the y-axis, day of water year relative to October 1st. And you see these curves here. These are the mean and median snow depth over the course of a typical year for this time period. And there's some noise up here in the maximum values and the minimum values. For some of the longer records, those really start to smooth out a little bit. We just keep plowing through this. What I'm doing here, I'll plot the current year. So basically where these black dots are the 2021 record, and you see, we were doing okay up here. We kind of got a little bit above the median, but during the ablation season, we were definitely below what is a mean snow depth for this particular sensor. Go down here. This was just to look at the percent normal. That was particularly good year, or particularly good day, April 1st. Here's an example of how to index it. And if you wanted to look at multiple sites, this is a little loop here that'll loop through, so you could do both of them and then plot them up together. You can see there's some bad values in there. These sensors are not perfect, but these are the two Grand Mesa sites. You can see that the snow depth is a little bit less at this one relative to that Park Slope one. And I think I just threw in Damagrath, I think, or the GPR tutorial has a bit more on correlation, so you can read about it there. But this was just looking at how close these two are on the same day. Pretty close to a 1-to-1 representation here, and then this is just looking at the correlation coefficient of 0.97 or so. So pretty good. It makes sense. These two sites are pretty close to each other. They're getting the same storm systems, the same snow coming in. But one of them is higher elevation than the other, and there are other factors that would lead to slightly different snow depths at the two sites. So there you have it. That's the SNOWTEL query. And the final thing I will say is there is this, within the geospatial tutorial, there's this geospatial cookbook rendered notebook. It won't run out of the box, but this was me scrambling to throw together a whole bunch of snippets of code to dynamically fetch DEM data, do some sampling of points. It won't run out of the box, but there's some samples there. I was hoping to clean this up, but I didn't have time. So peruse this on your own. Here's an overview of what's in here. And I actually did throw in one. This is one of our preliminary worldview DEM snow depth maps for Grand Mesa. This one is from 2017, I believe. And Dan McGrath did some initial analysis in this paper here. So I will leave it at that. That's there if you want to play with it.